Hey guys, Mr. Backerberg here. In this video, we're going to look at the power rule for arbitrary real powers. So now using everything that we've learned, we can finally prove the power rule in its final form. So if we have x being raised to the nth power, we can use some exponential and logarithmic things to help us rewrite this. And we can actually rewrite x to the nth power as e raised to the nth power times the natural log of x. And then based on that, we can use what we know about exponential derivatives and natural log derivatives to help us find the derivative of this x to the nth power. So if we want to take the derivative of this e raised to the n times the ln of x, what we're going to do with that, we'll have to do some chain rule stuff. But first, doing the derivative of e to the n times the ln of x, that exponential stays the same. So that becomes e to the n times the natural log of x. But because of the chain rule, we also have to attach the derivative of that top power piece. So in this case, n is just an exponent, a number. So n is going to stay the same. And then we're going to have to multiply that by the derivative of the natural log of x, which is 1 over x. Now from earlier, we said this e raised to the n times the ln of x. We said that came from x to the nth power. So I'm going to re-substitute that back in here for that e exponential. So then this is going to say x to the n times 1 over x. And I'm going to do a little rearranging. I'm going to take that n and move it to the front here. So it's going to be n times x to the nth times 1 over x. Now what we're going to be able to do with this is a little canceling. We have this 1 over x, but then we're multiplying by some x's in here. Now this is an x to the first power. When we do this canceling here, we would technically subtract the powers. So we've got n times, if we take this n and subtract that 1 power, that gives us x raised to the n minus 1 power, which is just the power rule. Now, as we're doing power rule things, we do want to remember that the chain rule is always a possibility. So if our equation was something like y equals some differentiable function u raised to an nth power, then as we're doing this derivative in here, we would still drop that power down, and we would subtract 1 from that power. But then, since u itself is a differentiable function, we would have to attach whatever the derivative of that inside function is, whatever the derivative of u is. So say we've got the equation y equals x to the square root of 2 power, and we want to find the derivative here. So using the power rule, we would drop down that square root of 2. We don't have to do anything with the x. That's going to stay the same. But then we'll have to subtract 1 from that power. Now, it's not real easy to take 1 away from the square root of 2, so we're just going to write it as root 2 minus 1. And we're just going to leave our answer like that. We don't really have to do any chain rule stuff because when we do the derivative of x, it's just 1. Technically, there's a times 1 on the end, but we don't have to put it there because if you multiply something by 1, it doesn't change the value at all. Taking a look at this example, we've got the equation y equals 2 plus the sine of 3x, all being raised to the pi power. So as we're finding the derivative in here, doing the power rule, we'll have to drop that pi down. Now we do have an inside function here, so we are going to have to do some chain rule stuff in just a second. But for now, we're just going to leave that the same. We will have to subtract 1 from the power, so I'm going to do pi minus 1. Now we have to attach the derivative of the inside stuff. The derivative of 2 is 0. I'm not going to put the 0 in here. Plus, now the derivative of the sine of 3x, this is going to be a double chain rule. The sine of 3x derives into the cosine of 3x, but then we're also going to have to do the derivative of that innermost function as well. So the derivative of 3x is just 3. Now we can rearrange this just a little bit. I'm going to take this 3 constant that's just floating on the end right now, and I'm going to bump it up front by the pi. So I'm going to call it 3 pi times 2 plus the sine of 3x being raised to the pi minus 1 power, all being multiplied by the cosine of 3x. Taking a look at this example, this one's a little bit different. We're going to be looking at finding a domain. So we've got the function f of x equals the natural log of x minus 3. We're going to find the derivative of f of x, and we're also going to state the domain of f of x. Now, as we're looking at this original function f, because it's a natural log, you're not allowed to do logarithms of negative numbers or 0. So as far as the domain for our f of x function, that's going to be x values that are greater than 3, avoiding 0 and negative numbers in there. We could also write this as interval notation, so going from 3 to infinity. So this is the domain for our original function f. Now, as we do the derivative of this function, since we're dealing with a natural log, when we do the derivative, it's 1 over whatever you're evaluating, so the x minus 3. Technically, we would want to do the chain rule here, but the derivative of the inside stuff is just 1, so multiplying this by 1 really wouldn't change anything. So I'm just going to leave it as 1 over x minus 3. Now, based on what we're seeing with this, because it's a fraction, it appears as if the domain would be any x value that's not 3, because we're used to looking for 0 on the bottom of the fractions, and in this case, 3 would give us 0 on the bottom of the fraction. But earlier, we said that our f of x function was not defined for any x values that are smaller than 3. And because of that, the derivative isn't defined for x values that are smaller than 3 either. So we don't want to use a domain of just x values that are not 3, but the domain for this derivative function also has to be x values that are greater than 3, or again, we could write that in interval notation going from 3 up to infinity. In this example, we're going to do something called logarithmic differentiation. So we've got the equation y equals x being raised to the xth power for x values that are greater than 0. We're used to doing power rule type stuff with powers that are numbers, but this power is another x. So we're going to need a different strategy here to help us find the derivative. So before we get to actually doing the derivative, what we're going to do with this equation, and I'm going to leave a little space in here, what we're going to do is take the natural log of both sides. Now on the left-hand side, that's just going to stay as the natural log of y. But on the right-hand side, because of the power property of logarithms, we're allowed to take this power that's up here and drop it down in front of our natural log. So that right-hand side turns into x natural log of x. Now we're going to go through and do the derivative implicitly because we have x's and y's in here. So on the left-hand side, when we're doing the derivative of the natural log of y, that turns into 1 over y, but because we're differentiating a y, we have to attach dy dx. On the right-hand side, because there's technically multiplying happening in here, we're going to have to use our product rule. So in this case, u is our x and v is the natural log of x. So based on the product rule, I'm going to leave the u value the same, which is just x, multiplied by the derivative of the v value, which is going to be 1 over x, plus, now I leave the v value the same, so the natural log of x, times the derivative of u, but the derivative of x is just 1, so multiplying by 1 doesn't really change anything here. Now in here where we have x times 1 over x, if we work on simplifying some things down, x times 1 over x is just 1. So the right-hand side is really just 1 plus the natural log of x. We want to get our dy dx alone. So where we have this 1 over y, I'm going to multiply both sides by y in order to get that dy dx alone. So this is going to say dy dx equals, I'm going to bump this y to the front, so y times 1 plus the natural log of x. But then we want to get things written in terms of x's. So earlier on, we said, based on our original equation, that y was equal to x to the xth power. So right in here where we have this y, we're going to replace that with x to the xth power. So this is really going to say x to the xth power times 1 plus the natural log of x. That thing is going to be our derivative for this function. Now, in our last example, we're going to look at tracking the spread of flu in a school. So this one says the spread of a flu in a certain school is modeled by the equation P of t equals 100 over 1 plus e being raised to the 3 minus t power, and P of t represents the total number of students that have been infected t days after the flu was first noticed. Some of those people may have already gotten well. This is just tracking the total number of infected. Now, there's a few different things that we're going to do with this equation. The first thing we're going to do is estimate the initial number of students that were infected with the flu. Your initial number happens when your t-value is 0. So we would just take this t-value of 0 and plug it into our function here. So really, this would say 100 over 1 plus e raised to the third power. And if we were to type all of that into our calculator, we would get approximately 5 students. So when they first noticed the flu at the time of 0, there were 5 students who were infected. Now, the next thing we're going to do is figure out how fast the flu was spreading after 3 days. So if we're trying to find the rate, we're going to have to find the derivative in here. Now, to do this, I'm going to do a little rewriting. I don't like having fractions in here because if we have fractions, then we have to do the quotient rule. I'm going to take this stuff that's on the bottom and swing it up to the top by making it 1 plus e to the 3 minus t, all being raised to the negative first power, because then I can apply the power rule instead of having to do the quotient rule. So doing the power rule, we would have to drop this negative 1 down and multiply it by the 100, so that becomes negative 100 times 1 plus e to the 3 minus t, subtract 1 from the power, and that becomes a negative 2 power. Now, because the stuff on the inside is actually a differentiable function, we're going to have to do the chain rule. So the derivative of 1 is 0, and if we do the derivative of e raised to the 3 minus t power, well, that just stays the same, e to the 3 minus t, but we're going to have to attach another chain because the power on that e is also a differentiable function. 3 derives into nothing. Negative t derives into negative 1. Now that negative 1 on the back end, along with the negative 100 on the front, turns into a positive 100, and I'm just going to copy down the rest of this stuff for now, but there is going to be one more change that I'm going to make. Looking at this stuff in the middle where we've got that negative 2 power, I'm going to put that down on the bottom of a fraction. So the 100 is going to stay on top. The e to the 3 minus t is going to stay on top, but this whole middle chunk is going to drop down to the bottom of the fraction, and that's going to turn that into a positive 2 power instead of a negative 2 power. So this is the derivative. We want to figure out how fast it's spreading after 3 days. So now we would have to plug in 3 for our t value. So this would say 100 times e. Now if we do 3 minus 3, that's going to be raised to the 0 power. On bottom, we're going to have 1 plus e. Again, 3 minus 3 is going to be raised to the 0 power, but that's all going to be squared. Now on top, e to the 0 power is just 1, so 1 times 100 is just 100. On bottom, e to the 0 power is 1, plus 1 is 2, squared is 4. So we have 100 over 4, which is 25. So that 25 means that the flu is spreading to 25 students per day. Now, the last thing we want to do is figure out when the flu was spreading at its maximum rate, and we want to figure out what that rate actually is. And what we're going to do is use the derivative to help us out. So on the previous slide, this was our derivative that we just ended up with. I'm going to graph this out, And if I'm looking for the maximum rate, well, this derivative represents the rate. So I would just want to find the maximum point on the graph of the derivative. So I've got my calculator fired up. In my y equals screen, I'm going to type in that derivative. So it was 100 times e being raised to the 3 minus t power. We're going to have to use x in here. And then on bottom, it was 1 plus e being raised to the 3 minus x power again. But all of that needs to get squared. I'm going to do zoom 6 on my calculator. I can't quite see the highest point on this curve when I hit graph, so I'm going to have to adjust my window a little bit. So I'm going to bump my Y max. Right now it's at 10. I'm going to bump it up to 50, and then I'll hit graph again. So I can see this bump in the graph in here. I want to find that maximum point. So I'm going to do second trace and go down to option number 4. That's the maximum. It asks for a left bound point, so we want to pick a point on the left side of this bump and hit enter. And then it asks for a right bound point, so I want to point on the right hand side of that bump, hit enter. We can take a guess, but we don't have to. I'm just going to hit enter again. So this says that the maximum is happening at an x value of pretty much 3. 2.99999 can get rounded to 3. And that maximum rate is 25. So that's actually what we just calculated. The maximum spreading rate occurs on that third day. And like we just calculated, it was spreading at a rate of 25 students per day. That's going to be it for this video. Thanks for watching.